Okay, this is AP lesson day 62. It's called hybridization, although it's really more of a continuation of VSEPR, the bond geometries the geometries of various molecules. And this is due on Tuesday after we get back from the Thanksgiving break. So as you can see, what I've done is I've given you problems from the book, assigned from Chapter 9, which is the chapter titled Molecular Geometry and Bonding Theories. And there is a set of books in class as well as the one that you have at home. So you should be able to complete this at home with the help of this video if needed. So let's get started. So page 183, number 92. So I'm going to be referring back and forth to the book and to the sheet that I'm writing on. So the first question is, if the three balloons shown on the right are all the same size, what angle is formed between the red one and the green one? That's question A. B, if additional air is added to the blue balloon so that it gets larger, what happens to the angle between the red and green balloons? And C, what aspect of the VSEPR model is illustrated in part B? So I'm going to show you how I want you to write these out. I won't necessarily write out all answers on this video completely, but I will expect you to do that. But the first one, let's go ahead and write it out completely. So it's 9.2a. All right. And the question was, if the three balloons on the right are all the same size, what angle is formed? So what's best to do is draw a sketch. So you have a balloon like this, a balloon like this, balloon like this. Your sketch doesn't have to be beautiful. So this is going to be 120 degrees, 120 degrees, and 120 degrees, even though it may not look it on my drawing, okay? So the angle, it was asking specifically for between the red and the green. So the angle, write out a complete sentence. What you're doing is practicing the way you're going to write an answer on the AP exam. Between the red and green Okay, and although it doesn't ask it, this would be the configuration of a trigonal planar molecule. It's three atoms and they're spaced equally 120 degrees apart. Okay, the next question is, if additional air was added to the blue balloon so that it gets larger, what happens to the angle between the red and green balloons? So what I want you to do is skip a line. So I'll count this as a line right here. So we're going to go to 9.2b. And what I'm going to do is draw a sketch of that. So now the blue balloon has gotten a lot bigger. So what happens to the red and the green? They get squeezed down so that their angle is less than 120 degrees. Okay, and just because you draw a drawing doesn't mean you don't write out the answer. So the angle between Okay, so the angle between the red and green balloons becomes less than 120 degrees if this one gets bigger. Okay, and then we're going to skip a line and we're going to go down to here, 9.2c. And presentation is not going to get you points on the AP, but it'll keep you from losing points on the AP. You want to be sure your answers are easy to read. So the last part is, what aspect of the VSEPR model is illustrated by part B? So if we draw part B again, and these just have to be kind of rough sketches. The larger blue balloon represents the space taken by lone pairs. I should say by a lone pair. And you can write that effect, lone pairs. You can use the word squeeze. It's not a technical term. Squeeze. The reduce might be a better word. Okay, so the larger blue balloon represents the space taken by lone pairs. In other words, it takes up more space. Lone pairs spread out because they're not held in place by another atom outside of them. And lone pairs squeeze the bonding angle, the bonding angle of the molecular bonds. Okay, so this is the way you should lay out an answer. Skip spaces. Don't try to save paper. Be sure it's presented neatly, and that's how we do that. And this should have been a C right here. Okay, so there you go. That's your answer for 9-2. All right, we're going to move on now. And 9-3 is the next one it's asked for. It says, an AB5 molecule adopts the geometry shown below. What is the name of this geometry? So let's just take these one at a time. Okay, so we go over to our sheet on pages 2 and 3 of our notes. There it is right there. So this is an octahedral electron configuration, your domain geometry, electron geometry, which is to say it's octahedral. It has 6 electron domains. 1, 2, 3, 4, 5 are bonding, and one of them is lone pair. And the shape is square pyramidal. In other words, it's the shape of an Egyptian pyramid. It has 4 sides to it, and it's a pyramid shape. Okay, so we're going to skip a line again. And the answer is, what is the name of the geometry? So this is, we'll just give it 2 names. The domain geometry means what family does it belong to? And the molecular geometry, raise this up a little bit, it's a wider view. Again, get in the habit of complete sentences. Okay, so there you go right there. That's the answer to A. We go on to B. Do you think there are any non-bonding electron pairs in A? Well, yes, and you guys have a nice chart to use as a reference. So yeah, you have one non-bonding pair. So in this case, you could say, again, I want you to skip a line, 9, 3, B. There is one non-bonding pair. Okay, so there is one non-bonding pair on the bottom. All right. Why or why not? And why or why not? So the why is simply it's just simply the shape of this. You are going to have it's asymmetrical. And when it's asymmetrical, it implies that something is missing down here, that there should have been another axial electron bond there. So that would be why or why not is part of 2B. So there is an axial atom missing. Okay, so that's the why or why not. C, suppose the atoms B are halogen atoms. Can you determine uniquely to which group in the periodic table atom A belongs? If they are axial, okay, can you determine uniquely to which group the periodic table A belongs? That's the central atom. So let's try to piece this together. It says that they are halogens. That means they come from this second to last column right here. And we don't know which halogen it is, but it's one of these. But we know that it's going to have 7 valence electrons. So let's go ahead and see if we can draw that out. So this is going to be 9.3C. All right, so here we have some central atom A, and we know that it's surrounded by 5 other atoms. And I'm going to use dots here. And so this is B, and this is B, and down here is B, and another one on the bottom, and another one over here. All right, and we know they have to have octets. And this one last, but here on the bottom. Okay, so you have 5 B atoms, which all have octets. So that's a total of 40. That's a total of 40 electrons. Okay, and it looks like this one is going to have an extended octet. So it has 2, 4, 6, 8, 10. And then we saw it had a lone pair. We said it had a lone pair at the bottom. So that's a total of 42. So it's 40 electrons. Those are bonding. Stay on screen here. Those are 40 bonding electrons. And it has 2 E- that are lone pair. We said that in the previous 2 answers. So that means there's a total of 42 electrons. So if B's were all halogens, they each brought in 7 valence electrons because they're in the second to the last row. So that's 1, 2, 3, 4, 5 times 7 is 35. And that means to get to 42, you had to have 7 more. And so that means A had to bring in 7 electrons as well. So if A brought in 7, then the answer to the question is A belongs to the halogen group also. That was a nice challenge problem. And you'll bear with me if I'm off screen a little bit temporarily. Okay, so there's your answer. So let's go over that again. We said that the B's were all halogens. That means they're going to bring in 7 times 5. We don't know which halogen, that's 35. Okay, we said we had 1, 2, 3, 4, 5 bonds plus 1 lone pair. So the 5 bonds are each going to have, each of those B are going to have an octet around them. That's a total of 40. The lone pair adds 2 more, that's 42. We know that the B's brought in 35 electrons. That means the A, this was the B's, that means the A had to bring in 7 times 1 equals 7 to add up to 42 electrons that you had in that bond right there. So if A brought in 7, then it also has to be a halogen. All right, so this is the way I want you to write out your answers. Okay, so from this point on, I'm not going to write out the complete answers for you. I'll sketch out the answer, but I want you to answer in complete sentences. I want you to practice expressing this in your own words. So take my words, use them to understand the answer, and then write it out in your own words. Okay, so 9.4 is the next question. The molecule shown here is a diafluoromethane, and there's the formula for it, which is used as a refrigerant. Based on the structure, how many electron domains surround the C atom in the molecule? So 9.4a. So in this one, I'll just sketch out the molecule. So they have a fluorine up here, a carbon in the middle, and then a couple of hydrogens down here. So you can see 1, 2, 3, 4. So A is 4 bonding domains. Again, I want you to write that as a complete sentence answer to get credit on the assignment. Okay, this is not worksheets where you just fill in an answer. All right, so 4 bonding domains. And again, I'll probably be on and off screen, so just bear with me until I get an answer completed. And then B. Would the molecule have a non-zero dipole moment? The answer is get this adjusted a little better. Okay, so non-zero dipole moment. The answer in a word is no. Highly electronegative fluorine pulls the electrons towards it. Okay, this is the most electronegative element on the periodic table, so the electrons are going to be pulled up towards these fluorines. All right, and then see if the molecule is polar, what is the direction of the overall dipole? So let's use our vectors. So I'm going to grab a red pen here, and I should have drawn these a little more evenly, these lines. They should both be going up at the same angle. And that's significant because I'm going to draw a vector here. The electrons are being pulled in the direction of the red arrow. So if we break those into components, we have one arrow going this way and one arrow going this way. And then we also have on the y-axis an arrow going up, and on this y-axis an arrow going up. So I'm taking this vector and breaking it into these two components right here, and I'm taking this arrow pulling towards the fluorine and breaking into these two. So these two cancel out because they're equal and opposite. but these two add together, so you have a net upward dipole like that. Okay, so the answer to 94C is there is an upward dipole. It's not in the direction, the dipole is not in the direction of the fluorines. Okay, it's not straight at these fluorines. It's what you do when you sum all of these components, it's straight up. The dipole is straight up for this molecule. Okay, so write those out in complete sentence answers. Okay, 9.5. The plot below shows the potential energy of two chlorine atoms as a function of distance between them. A, to what does an energy of 0 correspond in this diagram? So what we need to do is go to the very last page of your VSEPR notes that you got last week. This is the new edition, the color copy that I gave you. If you use the black and white, you're not going to see what I'm about to show you. So that's something that I added on. So we're going to go, it's on the very last page, and you can see this from the reading of the notes, and going to zoom out a little, and we're going to read this together about what these diagrams mean. This is the type of diagram that they're talking about. Okay, so this is the type of diagram. In this case, it's for a hydrogen atom. They're talking about chlorine. It doesn't matter. It's the same concept. Okay, hydrogen gas does not exist as separate atoms, but rather as diatomic molecules. This happens because as an H2 molecule, hydrogen is at lowest potential energy and therefore most stable. So hydrogen wants to exist as an H2 molecule. You don't find just hydrogen atoms floating around in space. They always want to pair up and form a molecule, and that's because they're more stable and at a lower potential energy at that state. So this represents what hydrogen atoms separated from each other are. They're at 0 potential energy. Just like electrons being separated from an atom, when you separate two hydrogen atoms, they have no pull or no effect or no energy on each other. We're only interested in the energy they have on each other. So that's 0 when they're a long ways apart. As you bring them together, they're attracted to each other. And why would that be? Well, why that would be is because if you look at what a hydrogen atom is, and we're on question 9.5, so I'm going to go ahead and draw that in question 9.5. A hydrogen atom is simply a proton and an electron. And when you can put two of them together like this, so you have another hydrogen atom. So basically, here's the electron cloud for this hydrogen atom. It's right here. And here's the electron cloud for this hydrogen atom. It's right there. These electrons attract the protons, and the protons attract the electrons. There's a mutual attraction for everybody. This proton even attracts the other hydrogen atom's electron, and this proton attracts the other hydrogen atom's electron. So they're very stable like this. This 2 proton, 2 electron configuration is more stable than just a single proton, single electron. It's at lower energy. They basically are hugging each other, these 2 atoms, and they like to be together. So what happens then is their potential energy lowers, and things like to exist in general in nature at the lowest possible energy. And there's even an exact distance that they know, and it's 0.74 picometers, which is, let's write down what that is. That's 10 to the minus 12 meters. That's what a PM or picometer is. So at 0.74 times 10 to the minus 12 meters, hydrogen is at its most stable, and this axis over here represents the energy, and you realize you're in negative energy down here. There it is right there. That's the most stable energy. Now what happens if you naturally start pushing these 2 hydrogens closer together so that these 2 nuclei got closer and closer together? Well, that's not natural for hydrogen. All of a sudden, these protons start to want to repel each other. And you're squeezing these electrons into too tight a space. Even though they can buzz all around, everybody's getting too tight. It's kind of like when you talk to somebody, you kind of want to keep your space. You don't want them too close to you, but you don't want them too far from you either. There's a comfortable space when you talk to somebody. And 0.74 picometers is where these two protons are comfortable. But if you were to force them together, what happens now is it's like pushing on a spring. It's starting to get harder and harder to push on that spring. The spring's pushing back on your hands. And so the energy goes up and up and up. And if you get them too close together, then it actually goes into positive territory. That means they're really repelling each other. Okay, so this is the point where those two protons are really starting to push away from each other. It's not natural. If you were to let them go, it'd be like letting go a spring, and they would spring back down to this distance right here. So this is the natural distance for them to want to separate. So just remember, zero energy is when they're so far apart they don't even feel the attraction of each other. As they come closer, they like each other, they want to get together, so they're in a more stable form. They get lower and lower potential energy until they're at the perfect distance right here. This is where they want to be. This is an H2 molecule. And then if you keep forcing them together, the potential energy is going to go back up, back up, back up, and it'll actually go up theoretically to infinity if you got pushing them closer and closer together. Okay, so that's what this question is dealing with. So let's continue with the question then. All right, so the question A is, what does the energy of zero correspond to in this diagram? So the answer is zero energy is complete separation of the atoms. Okay, this one I am kind of answering entirely for you. And in this case, they're Cl atoms. Both diatomic molecules. Homonuclear, same nucleus, diatomic molecules. Okay, next, B. According to the valence bond model, why does the energy decrease as Cl atoms move from a large separation to a smaller one? And that is that they seek lower energy. They seek lower energy, so they're more stable, okay? So I'm just, again, I want you to put this in your words. They're more stable when two protons join with two electrons. Okay, that's just more stable for them. They have a bigger attraction to each other there than if they're by themselves. Okay, 9.5 C. What is the significance of the CL-Cl distance at a minimum point in the plot? Okay, so this is the point. And you should write this as a complete sentence. I'm not writing a complete sentence. I'm giving you just an answer here. This is the point of lowest potential energy. And it's the most stable distance. Okay, and it's the most stable distance, okay? All right, D. What does the energy rise at CL-Cl distances less than at the minimum point in the plot? Why does the energy increase? Because of what we just talked about, repulsion, of the protons if they are too close together. Okay, and finally E, how can you estimate the bond strength of the chlorine-chlorine bond from this plot? So that would simply be, if we go ahead and just roughly reproduce that curve, where this is 0 right here, and we saw it comes in, it goes down, and then it comes back up. So this level right here is the bond energy. Remember, it's a negative number. It's some negative number. Let me get on screen here. It's some negative number. This is the bond energy down here. This is 0. It's some negative number. So let's just say that this number is negative x. I'm just saying it's some number x. So it would require positive x joules, I'll spell it out, of energy to break the bond. That would separate those two atoms apart from each other again, bring them both to 0 energy, so they were separated. Okay, and that takes care of that question. Okay, we're now on 9.6, so let's read it down here. See if I can bring it in a little closer. Okay. So 9.6, shown below are 3 parts of hybrid orbitals with each set at a characteristic angle. For each pair, determine the type or types of hybridization that could lead to hybrid orbitals. So we're getting a little bit into hybrid orbitals here. So let's go over to our sheet. And let's look at the first one. It's got a 90-degree angle. Remember, it's just part of a hybrid orbital. So there's a number of things that could have 90-degree angles. None of them on the front side of your sheet on page 2. There's 180, 120 for trigonal planar, less than 120, 109 for tetrahedral. We're going to go to the other side right here. And there you see that trigonal bipyramidal has some 90 degree. Not all of them are 90, but between the axial and the equatorial here is 90 degrees. If you come down here, this is actually not 90 degrees, even though T-shape looks 90 degrees. These lone pairs are pushing this down. So these are less than 90 degrees right here, these two angles. But when we get to octahedral, those are all 90 degrees. Every single angle in there is 90 degrees. So an octahedral or a trigonal bipyramidal could be the answer to this one right here. So go ahead and sketch it out real quickly. So just show this, and this. Remember, the SP hybrids or any of the hybrids look like bowling pins. So there you go right there. And they said that this is 90 degrees. And so that's trigonal bipyramidal. And this one is octahedral. So those are the two that are possible for the first one. For the second one, it's 109. That's a characteristic angle that you'll get used to hearing. And it is characteristic of tetrahedral. And where do you find that on the sheet? Come over here, and there it is right there. Tetrahedral is a 109.5 angle when it has all 4 domains bonded to atoms. Okay, if you take away one and have a lone pair there, then it becomes less than 109 because these three get pushed downward by the lone pair. So that's a concept we'll keep repeating. Lone pairs push down on the bond angles of the other bonded domains. Okay, so this one would simply be tetrahedral. And finally, the last one here is 120. And that would be trigonal planar. And where do you find that? That's right here. There's trigonal planar, 120 degrees. The other place you're going to find it is between the equatorial atoms on a trigonal bipyramidal. Between these three that are in the middle, those are 120 degrees apart as well. So we can put both of those down as possible answers. Okay, so there you go. There's your three answers, but I want you to write those out as complete sentences. Okay, that's 9-6. Okay, so now we're on 911A, or 911, and so it says an AB molecule is described as linear and the AB bond length is known. So let's first address this. What does AB mean? In this class, what we've been using is AX notation for the generic formula for a bond. So for, say, carbon dioxide, it would be AX2E2. Just go back to your sheet, your chart, and you would see for carbon dioxide, it would have that configuration. So this, for example, would be CO2. For H2O, it would be A, and I take that back. I made a mistake there. That should be E0. Okay, there's no non-bonded pair. So let me get the sheet out and be sure you're clear on this. So right there, carbon dioxide is AX2E0. It's linear, and so that's carbon dioxide. For water, it would be AX2E2. Because water has two lone pair electrons attached to it right there and there. Those are the E2s, and then the X's are the actual bonding pair right there. The notation the book uses for both of these, though, is it's simply called an AB2 molecule. They leave off the E part of it, and so both of these have the same notation. They just use the AX part of it. And it's an alternate notation. I happen to like this notation better because it shows you explicitly that these are not the same. These two make them look like they're the same configuration, same geometry, everything, whereas these two make it clear they're not because these lone pairs change the shape of a water molecule. So anyway, your book uses the AB notation, and we don't. So you understand what that is. So question is, does this information, it said the AB molecule is described as linear and the AB bond length is known. Does this information completely describe the geometry of the molecule? I'm not sure this answer is in your notes. It is in the book, but so I'll write this out as a complete answer. That is the geometry of a molecule. So let's just learn it right here. The geometry of a molecule is completely described by the bond angles and bond lengths. Okay, so you can just take that and put that in your information bank if it's not in the notes directly. Bond angles and bond lengths completely describe the geometry of a molecule. Okay, B, can you tell how many non-bonding pairs of electrons there are around the A atom? And this is where our notation is superior. If you use the AX notation, you can tell that there's two. If you just use AB notation, you can't tell here. So the answer is no, not from this notation. You can't tell that whether there are non-bonding electrons, those are lone pair electrons or not. But from the notation we use in class, you can. But the answer to their question, since they use this notation, is let's just write it out. What I just said. So the AX notation describes non-bonding non-bonding number of electrons. It should be number of non-bonding electrons. But the AB notation and excuse me if I'm off screen temporarily, does not. Okay, so that's it. The AX notation describes the number of non-bonding electrons, but the AB notation does not. Okay, and we're going to move on now to question 912. So let's read that one. And it says 912A, methane and the perchlorate ion are both described as tetrahedral. What does this indicate about their bond angles? Okay, so again, I'm going to give you the quick answer. You write it out as a complete sentence. Go to your chart. And the answer is 120 degrees. Write out a complete sentence answer, just like it was the AP exam. All right, that's A. B, NH3 molecule is trigonal pyramidal, but BF3 is trigonal planar. Which of these molecules is flat? Well, that's should be an easy question for you by now. Just go to your chart, and the name really answers that question. Trigonal planar is flat. Okay, trigonal pyramidal is a pyramid. Okay, it stands up. So that's the answer to that. Again, don't write your answer like this. I want you to write complete sentence answers like it was the AP exam. All right, we're going to keep moving. And we're now on 915 down here. How many non-bonding electron pairs are there in each of the following molecules? Okay, the first one's the trickiest. So let's go ahead and figure that out. So that's going to be 9.15. And it's A. Okay, so it's CH3, and then it's telling you have two of those. And then you have a sulfur there by itself. That's kind of an unusual configuration, but it's not so hard if you think about it. Think about what the geometry of that would look like. That should be CH3 2. That's very important, the 2 there. It means you got two of these. So let's draw one. So it's going to look like CH, H, H. But it says we have two of them. And we see we have this sulfur stuck in there somewhere. It's kind of an oddball. So if you had to guess and want to draw this, because your first guess at drawing any molecule is that it's symmetrical. So we're going to have another one of these. So I'm going to guess that it's over here, and it's going to be CH. It just forms a mirror image of the first one like that. And then a logical place for that sulfur to be is right here. Okay. Do I know that? No, it just seems logical that that's the way you would draw this. It may not be obvious to you at first, but that's what would be logical. So how many electrons do we have? So for C, we have 2 times 4 equals 8. For hydrogen, we have 6 times 1. You got 3 there, and then you multiply the whole thing by 2. So 6 times 1 equals 6. And then sulfur, For sulfur, you also have 6. So you have 1 times 6 electrons equals 6. That's going to give you 20. So let's go ahead and put single bonds between everything and see how many we use up. Okay, so we have 8 there and we have 8 over there. That gets us to 16. We need 4 more. So, and sulfur doesn't have an octet, so 2 go up there, 2 go down there. So that pretty much wraps that up. Okay, so that's what it looks like. So now let's see what the question is asking. It's asking how many non-bonding pairs are in each of the following molecules. And the only that we see are right here and right here. So the answer to that for A would be 2 non-bonding. Okay, and let me raise this up a little so you can see the whole thing. So there's the complete answer. There's the complete answer right there. Okay, let's go on to the next ones, and they seem a little easier. HCN. Okay, so this is 915B. And this one we've done in class. Hydrogen cyanide, and it looks like this. Okay, we do that from memory. Again, if we count our atoms, we have 1 hydrogen times 1. C is 1 carbon times 4. Nitrogen is 1 nitrogen times 5, and that gives you 10. And there's your 10 electrons right there. Okay, so the question is, it's asking how many non-bonding electrons are there. Well, they didn't say on the central atom, which is usually what we're interested in. So if they're talking about the central atom, there's none. There's no non-bonding on the carbon, but there is 1 out here. I don't know whether we want to count that or not, so I'm just going to say 1. Usually we don't care about non-bonding electrons that are on a terminal atom, on the outside of a terminal atom. So we're just going to say 1 there. The answer might be 0. In fact, I'm going to go to the solution manual on this one and see what they say. Yeah, they are. They're counting this one. So yeah, so they are counting non-bonding on the outside, but generally when we're talking about doing molecular geometries, we only care about the non-bonding that are on the central atoms. Okay, 915C. And what's that going to be? H2C2. Again, we're going to draw that symmetrically. And we'll just count quickly. You got 2 carbons times 4, and then hydrogen, so you got 10 electrons total. Okay, so what's that going to look like? You got a pair there, you got a pair there, you got a pair there. Okay, and then we need 10, so we need a couple more there, a couple more there. So now everybody has an octet. It's a triple bond. So non-bonding pairs is 0. So there are no non-bonding. Okay, next is CH3F. So what's that going to look like? Well, C is going to be in the middle. H is going to be here. If you go back to your bonding rules for covalent bonds, both hydrogen and fluorine can never be a central atom. They're always terminal atoms. So it's going to look like this. So fluorine is going to be 1 times 7. It's a halogen. Carbon is 1 times 4. Hydrogen is 3 times 1. That's going to give you 14. So we're going to put single bonds around. That's 8. Okay, and then you're going to complete the octet around fluorine, and there's 14 right there. Okay, so it has 1, 2, 3. Since they're counting them on the terminal atoms, it's 3 non-bonding. Right there. Okay, and that's it. Okay, so now we're on to 919. Again, I'm just following these problems right here on your assignment, and we've done everything up until here, 919. By the way, I'm going to tell you right now, we're not going to do 949. That really gets deeply into hybridization. I want to cover that in more detail in class on Monday after we return from break. So scratch that one for this assignment. We'll do that one later or something similar to it. Okay, so 919. It says, give the electron domain and molecular geometries of a molecule that has the following electron domains on its central atom. So it says 4 bonding domains and no non-bonding domains. So this is really easy. You just come to your chart and we go over here and we look for, that would be AX4, those are bonding domains, E0, those are non-bonding. So it's 4 bonding and no non-bonding, so it would be AX4E0. So that's tetrahedral, tetrahedral. So this is really, with your chart, this becomes a really easy question. Okay, so go ahead and write out the AX notation for that. And it's tetra and tetra. Okay, for B, and I want you to skip a line between every question. All right, it's 3 bonding and 2 non-bonding. Again, just come back over to your table, and you're on the back side this time, and it's 3 bonding and 2 non-bonding right there. So that's going to be this. It basically started off like this, and you pulled off 2 of those equatorial models. So it's trigonal bipyramidal, and T-shaped is the actual molecular geometry. This is the family that it belongs to. All of these are trigonal bipyramidal. And this is the actual geometry. It looks like a T. So go ahead and write the AX notation for that again. Trigonal bipyramidal and T-shape. Okay, so there's the answer for that. Okay, now to C. And C is 5 bonding and 1 non-bonding. So you come over here, there it is right there. It's part of the octahedral family, but it's lost one of the atoms, so there's a lone pair there. So the actual shape is square pyramidal. AX5E1. So there you go right there. Okay, octahedral and square pyramidal. D. Is there a 919D? Oh yeah, there's. Okay, they skipped from C to E. That's very strange. So anyway, even textbooks make mistakes. 4 bonding domains and 2 non-bonding domains. So we'll call that E since they decided to call that E. Okay, so it says 4 bonding and 2 non-bonding. So you come down here to the very end. There's an AX4 bonding and 2 non-bonding, so it's an octahedral family, and it's a square planar molecular geometry. And there it is right there. Okay, so that takes care of 919. Let's move on now. The next one on our sheet is going to be 921. Okay, down here, so let's read that. It says, give the electron domain and molecular geometries for the following molecules and ions. So you're going to have to draw the Lewis dot on these and then just go to the chart. All right, so let's go ahead and do that. HCN we've already done. And it looks like this. Okay, so our AX notation for this is there's two bonding domains. And it doesn't matter whether it's single, double, or triple bonds. This is one bonding domain. Domain means location. It's one location of a bond, even though there's a triple bond here. So that's going to be A. There's two bonding locations, X2. And on the central atom, we don't care about this anymore like we did on that previous problem. The central atom, we don't have any lone pairs, so it's E0. So that's going to be linear electron domain geometry and linear molecular geometry, the actual shape. Anytime you have an E0, these two names are going to be the same. All right. And what else did it ask us to do? That's what it asked us to do. Okay, let's go to skip a line. Don't write stuff over here for a different problem. Just use paper, okay? Make things, lay things out so they're easy to see, easy to follow. 921B, and that's going to be SO3 2 minus. Okay, I don't think we haven't dealt with that one before, so let's draw it out. SO3 2 minus. So how many electrons is that? Sulfur, there's one atom times 6 electrons. Oxygen, there's 3 atoms times 6 electrons. And then E minus by itself, there's a 2 minus charge, so that's simply going to be 2 more electrons. And if we add those up, we get 26. Okay. And sulfur is going to be less electronegative than oxygen. We're going to stick that in the middle. And since we don't know any better, we're just going to assume it's linear. Just make it a nice symmetrical shape. And we need to fill in 26. So there's 2 there, there's 2 there. And then we're going to fill in octets around everything here. Oh, it's SO3, my bad. So let me just put another O up here. So right there, you've used 24 and you need 26, so you just stick them right there. Okay, so what we're interested in is what's surrounding this central atom. So it's got 3 bonding locations, domains, and 1 non-bonding domain. So that's going to be an AX3, those bonding locations, and the lone pair is E1. So you just simply come to your chart and translate it. Okay, so it's right here. So it's tetrahedral because it has 4 electron domains in all, but one of them is missing, so it becomes trigonal pyramidal. So this is not flat. It's shaped like a pyramid where this is higher. This pink one is higher than these 3 white ones, so it's a 3-sided pyramid, trigonal pyramidal. All right, so that's your answer right there, tetra and trig pyramidal. Okay, so there's the complete answer for that right there. Okay, let's keep going. The next one is SF4. So I tell you what I'm going to do for you. Do you a little favor here. I'm going to stop the video and just write these down and just start it up when I have them all down, and that'll save us a little time. Okay, so the next 4 and 921, I'm going to go through a little bit quickly. So the next one we have is SF4. You count the electrons, you have 34 electrons. Logically, you would put the S in the middle. You have the fluorines around it. Everybody gets an octet. That leaves you with 2 extra electrons, and that's going to be a lone pair on the central atom. That's what you do when you have the extra ones, and they're in the 3rd row or below. So that's going to be an AX4 because there's 4 bonding domains with the fluorines, and E1, that's the lone pair. So go to your chart. Right here, there it is, AX4E1, and that's trigonal bipyramidal for the domain geometry, and then the actual shape is the seesaw shape right there. Okay, so there you go right there. Next is PF6. You add all those electrons up, you end up with 48 electrons in all. I used kind of a shorthand I use when I'm in a hurry. I don't want to draw 48 dots. It's messy. You get confused where the dots are. So I just circle them if they have complete octets like that. Don't do that on the AP, but you can do it here. So anyway, that's 8 times 6 is the 48. That's what I needed. So it's AX6E0. There's no lone pairs left over. So that's octahedral, domain geometry. Next one up is an NH3Cl. And if you count that, it has 14 electrons. You add up the electrons from nitrogen, hydrogen, chlorine, and then you subtract 1 because it's a cation, has a positive charge to it. So there's 14 electrons. Again, this is just the symbol for electrons, E minus. And so there's 14. This is the way it would look. So you can see it has 4 bonding domains and no lone pairs. So that's AX4E0 tetra for that one. And finally, N3 minus. So each nitrogen has 5. 5 times 3 is 15. And then you got an anion there. So you add 1 more to make it 16. And you'll end up with a triple bond on one side and a single bond on the other. But the point is there's 2 bonding domains there. So it's AX2E0, and that's linear. Okay, so we still have a few more problems left on this assignment. I'm going to wrap this this particular video right here and continue with the rest of the problems on a new video, but I'll go ahead and publish this and you'll have that up to at least get started on the assignment. And I'll see you on the next video.